Imagine you float weightless within infinite smooth darkness, moment before time began. Year 13.799999 billion BC. No light exists, no matter, no space, just quantum vacuum fluctuations whispering across Planck scales 10 to the power of minus 35 meters. Temperature equilibrium hovers 10 to the power of 27 Kelvin across formless potential. Space-time geometry uncertain, ripples forming, unforming eternally. Somewhere within infinite possibility, single gravitational instability begins patient growth. Density perturbations 1 part in 10 to the 5th slowly amplify. Singularity approaches not with violence, but inevitable condensation. Fundamental forces strain toward unification. Reality prepares emergence from quantum dream state. Cosmic potential breathes, expansion coefficient approaches infinity, inflation field stirs. Birth approaches across all existence. Good evening, welcome back. New listeners, welcome. Tonight, perfect cosmic rest. Find comfortable position. Dim lights completely. Adjust pillow beneath neck, perhaps soft white noise mimicking cosmic microwave background 2.725 Kelvin hum. Let breathing slow, matching universe expansion rate 73 km per second per megaparsec. Perfectly safe drifting among galaxies. Tonight slowly explore complete universe history. First Planck, second 10 to the power of minus 43 seconds through 13.8 billion years. Cosmic evolution toward heat death. Equilibrium trillions years future. Watch plasma soup cool forming first atoms. Witness population 3 stars patiently ignite. Observe galaxy formation cosmic web assembly. Trace planet formation solar system birth. Contemplate life emergence. Earth pale blue dot. Witness galactic evolution. Milky Way maturing, peer deep future, proton decay era, black hole evaporation finale, dark energy dominance isolation. Long, slow cosmic journey told maximum atmospheric detail, perfect drifting across space-time. If cosmic timescales help restful sleep, consider like or subscribe. Curious stargazing location. Comment city time zone. No pressure whatsoever. Just cosmic relaxation. Now you find yourself suspended within the Planck epoch, those first incomprehensible moments between 10 to the power of minus 43 and 10 to the power of minus 36 seconds after existence began. Time itself uncertain here, space-time woven from quantum foam, roiling at scales smaller than anything imaginable. Every Planck length, roughly 1.6 times 10 to the power of minus 35 meters, represents fundamental pixel of reality, smallest possible distance before geometry itself loses meaning. At this scale, space-time bubbles and froths like cosmic champagne, virtual particles popping in and out of existence following Heisenberg uncertainty principle, borrowing energy from vacuum for infinitesimal moments before returning it. Temperature hovers around 10 to the power of 32 Kelvin, so impossibly hot that thermal energy per particle exceeds energies we'll ever reach in particle accelerators by factors of millions. At these temperatures, all 4 fundamental forces, gravity, electromagnetism, strong nuclear force, weak nuclear force, merge into single unified superforce. Physics as we understand it doesn't yet exist. No distinct particles, no clear separation between forces, just unified field pulsing with incomprehensible energy, density approximately 193 grams per cubic centimetre. If you could hold teaspoon of this primordial substance, though concepts like hold and teaspoon remain meaningless here, it would outweigh billions of galaxies. Gravitons, hypothetical particles carrying gravitational force with spin 2 propagate through churning geometry. These messengers of gravity, never yet detected in our modern universe, swim freely through space-time soup. String theory whispers possibility that fundamental ingredients aren't point particles, but tiny vibrating strings, each oscillating at specific frequency-determining particle properties. Perhaps reality's smallest components are these strings, each roughly 1 Planck length long, vibrating like cosmic violin strings, producing all particles and forces through different resonance patterns. M theory suggests 11 dimensions exist here, though we perceive only 3 spatial dimensions plus time. 7 extra dimensions curl tightly into Calabi-Yau manifolds, complex geometric shapes smaller than atoms, influencing physics through hidden geometries. These extra dimensions shape how forces behave, determining strength ratios between electromagnetism and gravity, between strong and weak nuclear forces. Our entire physical law structure emerges from these dimensional geometries we cannot directly perceive. Quantum fluctuations ripple across this formless potential, microscopic variations in energy density seeding all future structure. These aren't simple ripples, but intricate patterns following quantum mechanical probability distributions. Some regions infinitesimally denser, others slightly less dense. These variations, typically around 1 part in 100,000, will later determine where galaxies form, where cosmic voids stretch empty, creating large-scale structure, visible 13.8 billion years hence, when someone builds telescopes powerful enough to map universe's architecture. Space-time emerges gradually from quantum indeterminacy, transitioning from probabilistic quantum superposition states to classical definite geometry. Before this transition, asking where or when something happens carries no meaning. Reality exists as probability amplitude field, wave function, describing all possible configurations simultaneously. Then, through quantum decoherence and measurement-like processes we still don't fully understand, classical space-time crystallizes from quantum haze, like ice forming in supercooled water, sudden phase transition from quantum to classical behavior. You drift through this epoch watching fundamental constants establish themselves. Speed of light, Planck constant, gravitational constant. These values emerge from unified field symmetry breaking, like water molecules arranging into ice crystal lattice patterns. Values not random, but constrained by consistency requirements. Anthropic principle noting that we observe these particular values because only these allow complex structures like observers to eventually exist. Imagine watching quantum foam up close. At 10 to the power of minus 35 meter scales, space-time writhes and twists. Tiny wormholes open and close, connecting distant space-time points for 10 to the power of minus 43 seconds. Black hole and white hole pairs spontaneously emerge and annihilate. Causal structure uncertain. Effects sometimes preceding causes within these quantum realms. Topology itself fluctuates, space-time occasionally splitting or merging like soap bubble surfaces, 3-dimensional reality becoming 4-dimensional for brief moments before collapsing back. The Planck time itself, 10 to the power of minus 43 seconds, represents smallest meaningful time interval. Asking what happened before 1 Planck time requires understanding time intervals shorter than Planck time, but quantum gravity effects become so strong that space-time loses classical meaning entirely. Time becomes granular rather than smoothly continuous, possibly divided into discrete Planck time units like frames in film. though whether time is truly discrete or merely appears so at these scales remains debated among theoretical physicists studying quantum gravity. Supersymmetry might exist here, theoretical framework suggesting every particle has superpartner particle. Electrons have selectrons, quarks have squarks, photons have photinos. These superpartners haven't appeared in modern particle accelerators, possibly too massive to produce. But in this early universe's extreme energies, all supersymmetric particles dance freely. Supersymmetry would help unify forces, explaining how electromagnetic and weak nuclear forces already merged into electroweak force, and how strong force and electroweak force might merge into electronuclear force at these energies. You watch phase transition approaching. The unified superforce won't remain unified. As universe expands and cools, symmetry will break like freezing water, crystallizing into snowflake patterns. Gravity will separate first, becoming distinct force around 10 to the power of minus 43 seconds, Planck epoch ending. Strong nuclear force will separate next around 10 to the power of minus 36 seconds. Electroweak force will remain unified until much later, around 10 to the power of minus 12 seconds. Each symmetry breaking releases energy, driving further expansion, creating distinct force laws governing modern physics. Billions of years later, physicists will call this spontaneous symmetry breaking, same mechanism giving particles mass through Higgs field. Imagine perfect sphere rolling along flat surface. Infinite rotational symmetry exists, but sphere reaches hilltop and must roll down some direction. Moment it chooses direction, symmetry breaks. Similarly, unified field must choose which forces separate, how particles gain mass, which physical constants take specific values. These choices feel random, but follow deeper logic embedded in quantum field equations mathematicians still work to understand fully. Time passes, though passes seems wrong word. Duration between 10 to the power of minus 43 and 10 to the power of minus 36 seconds spans roughly 10 to the power of minus 36 seconds total. Yet this represents critical epoch, establishing everything following. Imagine watching paint dry seems boring. Try watching Planck Epoch, where nothing visible happens, yet everything foundational occurs beneath reality's surface. Fundamental forces arranging themselves into configuration, allowing chemistry, biology, consciousness emerge 13.8 billion years hence. Consciousness, now at 10 to the power of minus 36 seconds after beginning, temperature dropped to merely 10 to the power of 27 Kelvin, and you witness cosmic inflation beginning, brief period of exponential expansion stretching space-time faster than light speed. Inflation sounds impossible. Einstein's relativity forbids faster than light motion, but relativity prevents matter moving through space faster than light, not space itself expanding. Space-time can stretch at any rate. During inflation, space doubles size approximately every 10 to the power of minus 37 seconds. Incredibly rapid expansion, though each doubling happens smoothly, gently, like rubber band stretching, rather than explosion. Something Einstein might have found delightfully frustrating to reconcile. This expansion driven by inflaton field, hypothetical scalar field permeating space with large potential energy. Scalar fields, unlike vector fields with direction like electromagnetic or gravitational fields, have magnitude but no direction, filling space uniformly. Inflaton field sits in false vacuum state, high energy configuration unstable but slow to decay. While field remains false vacuum, its energy density generates negative pressure, causing space itself to expand exponentially. This negative pressure, opposite normal matter's positive pressure, drives universe outward relentlessly. Imagine inflaton field like ball resting atop hill. Ball wants rolling downhill to lower energy state, but hill very flat near summit, so ball rolls incredibly slowly. During slow roll, ball's potential energy drives inflation. Eventually ball reaches steep slope, begins rolling quickly, inflation ends, potential energy converts to particles, and radiation through process called reheating. Universe floods with particles as inflaton field oscillates rapidly around minimum energy state, dumping stored energy into standard model particles. Inflation typically lasts around 10 to the power of minus 32 seconds, ending approximately 10 to the power of minus 32 seconds after beginning. During this brief moment, universe grows by factor of at least 10 to the power of 26, possibly much more depending on theoretical model. Region smaller than Proton expands to size larger than observable universe today. Expansion so rapid that any initial curvature gets stretched flat, explaining why universe appears geometrically flat when measured precisely. Imagine crumpled paper stretched smooth. After sufficient stretching, local region appears perfectly flat, even if overall paper curved. Those quantum fluctuations from Planck epoch get stretched during inflation, microscopic variations expanding to cosmic scales. Regions infinitesimally denser than average become galaxy cluster seeds. Regions slightly less dense become cosmic voids. These density perturbations freeze into space-time as inflation ends, creating pattern cosmologists observe billions of years later in cosmic microwave background radiation. Hot and cold spots showing where matter concentrated and rarefied. Eternal inflation hypothesis suggests inflation never completely ends everywhere. While inflation ends in our observable universe patch, other regions continue inflating, spawning infinite bubble universes with potentially different physical laws and constants. Each bubble nucleates from quantum fluctuation, expanding into separate causally disconnected cosmos. We inhabit one bubble among infinite multiverse, though whether other bubbles truly exist or remain, mathematical abstraction continues debated. Our observable universe just tiny portion of one bubble among possibly infinite collection. Inflation solves several cosmological puzzles elegantly. Horizon problem, why regions of universe never in causal contact share identical temperature, solved because all regions originated from tiny causally connected patch before inflation stretched them beyond mutual light horizons. Flatness problem, why universe geometry so precisely flat, solved because inflation stretches any curvature away. Magnetic monopole problem, why predicted monopoles from grand unified theories never observed, solved because inflation dilutes monopoles to undetectable densities across vast volumes. You float through inflating space watching exponential growth. Each moment, space between any 2 points doubles. First moment, separation doubles. Second moment, now twice as far apart, that distance doubles again, becoming 4 times original. Third moment, quadruples again to 8 times. After just 100 e-foldings, 100 doubling times, initial distance multiplied by 2 to the power of 100, roughly 10 to the power of 30 times larger. Reality growing faster than anything within it could possibly communicate, causality itself stretched beyond recognition. Temperature drops rapidly during inflation, not because energy dissipates, but because space expands so quickly that thermal energy density decreases dramatically. Starting 10 to the power of 27 Kelvin at inflation beginning, Temperature plummets toward 10 to the power of 22 Kelvin by inflation end. This cooling purely geometrical, same energy spread across exponentially larger volume, naturally reduces energy density and corresponding temperature. Like stretching hot rubber band, expansion cools it. Quantum fluctuations during inflation behave peculiarly. Heisenberg's uncertainty principle guarantees that even inflaton field experiences quantum jitters, tiny variations in field strength at different locations. Normally these variations remain microscopic, but inflation's exponential expansion stretches quantum fluctuations to macroscopic scales. Microscopic quantum uncertainty becomes cosmic scale density, variations seeding galaxies and large-scale structure. Quantum mechanics, normally important only at atomic scales, suddenly imprints pattern across entire observable universe and beyond. As inflation ends around 10 to the power of minus 32 seconds, inflaton field rolls down potential hill into true vacuum minimum energy state. Field oscillates wildly around minimum, this oscillation energy converting into particles through parametric resonance and particle creation processes. Universe reheats, though not to initial 10 to the power of 27 Kelvin, but still incredibly hot around 10 to the power of 22 Kelvin. This reheating populates universe with standard model particles, quarks, leptons, gauge bosons. Matter as we know it emerges from inflaton field decay. Now you find yourself immersed in quark-gluon plasma, perfect relativistic fluid filling universe from 10 to the power of minus 32 to 10 to the power of minus 6 seconds after beginning. Temperature approximately 10 to the power of 22 to 10 to the power of 13 Kelvin across this epoch. Too hot for protons or neutrons existing yet. Instead, their constituent quarks and gluons swim freely through plasma, unconfined by strong nuclear force which at these energies cannot bind quarks into hadrons. Quarks come in 6 flavors: up, down, charm, strange, top, bottom. Though in this early universe primarily up and down quarks dominate, lighter quarks requiring less energy to produce. Each quark carries color charge analogous to electric charge, but with 3 values: red, green, blue. Gluons, strong force carriers, themselves carry color charge unlike photons which don't carry electric charge. This makes strong force behave peculiarly, stronger at larger distances, weaker at short distances, property called asymptotic freedom, discovered in 1970s earning Nobel Prize. The plasma behaves as nearly perfect fluid with extremely low viscosity, meaning it flows with minimal internal friction. Heavy ion collisions at modern particle accelerators like RHIC and LHC briefly recreate this primordial state. Quark-gluon droplets existing for 10 to the power of minus 23 seconds before cooling into hadrons. Experiments confirm plasma's perfect fluidity, viscosity to entropy ratio approaching theoretical quantum minimum, making it most perfect liquid ever observed. You drift through plasma watching quarks and gluons interact continuously. Strong force mediated by 8 types of gluons, each carrying combination of color and anti-color charges. Gluons themselves interact with other gluons due to carrying color charge, creating complex dynamics unlike electromagnetism, where photons don't interact with each other. This gluon self-interaction makes quantum chromodynamics, theory describing strong force, mathematically challenging, requiring supercomputers for precise calculations. At approximately 10 to the power of minus 12 seconds, temperature drops to around 10 to the power of 15 Kelvin, cool enough for critical phase transition, electroweak symmetry breaking. Before this moment, electromagnetic force and weak nuclear force unified into single electroweak force. After this transition, they separate into distinct forces we observe today. This symmetry breaking, mediated by Higgs, field permeating space, acquiring non-zero vacuum expectation value, giving particles mass through interaction strength with Higgs field. The Higgs mechanism works elegantly. Imagine particles moving through space filled with Higgs field like people walking through crowded room. Popular person constantly stopped by well-wishers, slowed down, effectively gaining mass through interactions. Unpopular person walks straight through unimpeded, remaining massless. Similarly, particles coupling strongly to Higgs field, top quarks, W and Z bosons, acquire large mass. Particles coupling weakly or not at all, electrons, photons, remain light or massless. Though black holes have no hair, according to no-hair theorem, the Higgs field apparently plays cosmic hairdresser, styling particles with mass. W and Z bosons, carriers of weak nuclear force responsible for radioactive decay and nuclear fusion in stars, acquire masses around 80 and 91 giga-electron volts respectively through Higgs mechanism. Before symmetry breaking, these bosons massless like photons. After symmetry breaking, Higgs field gives them substantial mass, making weak force short-ranged unlike electromagnetism, which extends infinitely through massless photons. This mass generation critical for allowing stars to shine properly billions of years later, weak force regulating hydrogen fusion rates in stellar cores. Higgs boson itself, quantum excitation of Higgs field discovered at LHC in 2012, would have existed in thermal equilibrium during this epoch, constantly created and destroyed through particle collisions. Modern universe too cold for thermal Higgs boson production. Only high-energy colliders or early universe hot enough. Finding Higgs boson confirms electroweak symmetry breaking mechanism, validating standard model, and earning Peter Higgs and Francois Englert 2013 Nobel Prize. Universe continues expanding and cooling. Plasma gradually thins as space stretches. Strong force coupling, constant increases as energy decreases, preparing for quark confinement phase transition approaching at 10 to the power of minus 6 seconds. Meanwhile, massive particles like top quarks decay into lighter particles within fractions of a second after production. Only stable particles like up quarks, down quarks, electrons, neutrinos, photons, gluons persist alongside transient particle-antiparticle pairs popping in and out of existence. You watch carefully as universe ages from 10 to the power of minus 6 seconds to 1 second. Hadron Epoch begins. Temperature dropped to approximately 10 to the power of 13 Kelvin, critical threshold where quarks confine into hadrons. Composite particles like protons and neutrons made from 3 quarks bound by strong force. This confinement phase, transition, represents fundamental change in matter's organization. Below this temperature, quarks cannot exist freely. Strong force binding becomes so powerful that quarks always found confined within hadrons. Protons form from 2 up quarks and 1 down quark. Total electric charge, positive 1. Neutrons form from 1 up quark and 2 down quarks, electrically neutral. These baryons, particles made from 3 quarks, suddenly populate universe, replacing quark-gluon plasma. Mesons also form temporarily, particles made from 1 quark and 1 antiquark, but most decay, quickly leaving mainly baryons and antibaryons. Matter-antimatter asymmetry becomes critical here. For every billion antimatter particles, roughly 1,000,000,001 matter particles existed, tiny imbalance of 1 part in billion. This asymmetry, called baryon asymmetry, encoded in parameter ETA, approximately 6 times 10 to the power of -10 measuring ratio of baryons to photons. When matter and antimatter annihilate, they produce photons. That tiny excess of matter survives annihilation, becoming all matter we observe today. Every atom in every star, planet, person. This asymmetry likely originated during earlier epochs through CP violation. Differences between matter and antimatter behavior observed in weak interactions, combined with mechanisms like leptogenesis or baryogenesis scenarios. Sakharov conditions specify requirements for generating matter excess, baryon number violation, C and CP violation, thermal non-equilibrium during phase transitions. Early universe provided conditions allowing these mechanisms to generate observed matter predominance. You watch matter-antimatter annihilation proceed. Protons encounter antiprotons, annihilating into photons plus pions. Neutrons meet antineutrons, similarly annihilating. Temperatures still high enough for particle-antiparticle pairs continuously created from photons, but universe cooling means pair production slowing while annihilation continuing. Eventually thermal energy drops below threshold for creating proton-antiproton pairs, around 10 to the power of 13 Kelvin. After this freeze-out, remaining antimatter annihilates with equal amount of matter, leaving only that tiny 1 in billion excess of matter surviving. Those surviving baryons, approximately 1 proton or neutron per billion photons, constitute entire matter budget universe possesses today. Every atom in your body, every star in sky, every galaxy across cosmos, all originated from that minuscule matter excess surviving annihilation. Antimatter effectively vanished from universe, aside from occasional antiparticles produced in cosmic ray collisions or particle physics experiments. Neutron-proton ratio becomes important. Initially around equal numbers of protons and neutrons existed, but weak interactions converting neutrons to protons and vice versa gradually shift ratio. Neutrons slightly heavier than protons by about 1.3 mega-electron volts, requiring more energy to produce, so as universe cools, neutron abundance decreases. Weak interactions like neutron decay, neutron becoming proton plus electron plus antineutrino, reduce neutron fraction, while reverse reactions become energetically unfavorable as temperature drops. Around 1 second after beginning, lepton epoch transitions in. Temperature approximately 10 to the power of 10 Kelvin. Electrons and positrons still abundant, created from and annihilating into photons continuously. Neutrinos, having decoupled earlier, now stream freely through universe, no longer interacting significantly with matter. These ghost particles, interacting only through weak force, travel unimpeded across cosmos, carrying information about universe's first second, forever encoded in cosmic neutrino background we cannot yet detect. Electron-positron annihilation becomes dominant process. As temperature drops below threshold for creating new electron-positron pairs around 10 to the power of 9 Kelvin, remaining electrons and positrons annihilate, converting their mass energy into photons. This annihilation reheats photon gas slightly, while neutrinos, already decoupled, continue cooling independently. From this point forward, photon temperature slightly exceeds neutrino temperature by factor roughly 1.4, maintaining this ratio through subsequent expansion. The electron excess, like baryon excess, ensures not all electrons annihilate. For every billion positrons, roughly billion and one electrons existed. After annihilation completes, that tiny electron excess remains, exactly matching proton excess. This lepton-baryon balance, not coincidental, but required by charge neutrality. Universe must contain equal positive and negative electric charge. If proton and electron charges didn't precisely balance to 1 part in 10 to the power of 21 or better, electromagnetic forces would tear matter apart immediately. You now approach 3-minute mark, universe cooling toward 10 to the power of 9. Kelvin, critical temperature for Big Bang nucleosynthesis beginning. Matter content simplified dramatically. Mostly protons and neutrons in roughly 7:1 ratio due to weak interaction freeze-out and neutron decay. Electrons balancing proton charge, neutrinos streaming freely, photons outnumbering baryons billion to 1. This dilute gas of simple particles about to build first atomic nuclei through nuclear fusion. Before nucleosynthesis begins properly, universe must traverse deuterium bottleneck. Deuterium, heavy hydrogen nucleus containing 1 proton and 1 neutron, represents critical first step toward building heavier elements. But deuterium binding energy only 2.2 mega electron volts, relatively weak. While temperature exceeds few billion Kelvin, high energy photons photodisintegrate deuterium nuclei as quickly as they form, splitting them back into free protons and neutrons. Only when temperature drops sufficiently do deuterium nuclei survive long enough to build heavier elements. This waiting period critical for nucleosynthesis outcome. Neutrons decay with half-life roughly 10 minutes. Longer universe takes reaching deuterium, stability temperature, more neutrons decay into protons, reducing neutron fraction available for building helium and heavier nuclei. Balance between cooling rate and neutron decay rate determines primordial element abundances precisely, predictions matching observations remarkably well, one of cosmology's greatest triumphs. Around 3 minutes, temperature finally drops to approximately 10 to the power of 9 Kelvin. Deuterium becomes stable against photodisintegration. Protons and neutrons begin fusing into deuterium nuclei through weak interaction plus strong force binding. Proton plus neutron yields deuterium plus gamma ray photon. Once deuterium accumulates, subsequent reactions proceed, rapidly building heavier nuclei through series of fusion reactions nuclear physicists map in exquisite detail. Deuterium nuclei fuse with protons forming helium-3, 2 protons plus 1 neutron. Helium-3 nuclei fuse with additional neutrons forming helium-4, 2 protons plus 2 neutrons. Alternatively, 2 helium-3 nuclei fuse, releasing 2 protons and creating helium-4. Multiple reaction pathways exist, but dominant channel produces helium-4, most tightly bound light nucleus with binding energy 28 megaelectron-volts, very stable configuration. Nearly all available neutrons end up locked inside helium-4 nuclei. With initial neutron-proton ratio around 1 to 7 after decay losses, approximately 1 helium-4 nucleus forms per 14 baryons total. This yields mass fraction roughly 25% helium-4, exactly matching observed primordial helium abundance in oldest stars and metal-poor gas clouds. This agreement between predicted and observed helium abundance provides powerful confirmation of Big Bang model. Trace amounts of other light elements also form. Deuterium survives at levels around 1 part in 40,000 by number. Helium-3 forms at levels around 1 part in 100,000. Lithium-7 appears at roughly 1 part in 10 billion. These trace abundances extremely sensitive to conditions during nucleosynthesis, particularly neutron-proton ratio and baryon density, allowing cosmologists to infer early universe properties from measurements of primordial abundances in pristine gas clouds. Nucleosynthesis essentially stops after about 20 minutes. Temperature dropped below 10 to the power of 8 Kelvin, too cold for additional fusion reactions, overcoming Coulomb barriers between positively charged nuclei. Elements heavier than lithium require hotter, denser conditions found only in stellar cores billions of years later. Universe emerges from nucleosynthesis era, composed roughly 75% hydrogen, 25% helium, trace deuterium and lithium. Simple mixture maintaining these ratios for hundreds of thousands of years until stars ignite. You drift forward through time, universe continuing expansion and cooling. Temperature steadily decreases, density drops as space stretches. For next 380,000 years, universe exists as hot plasma, electrons and nuclei swimming freely through photon sea. Thomson's scattering, photons bouncing off free electrons, keeps universe opaque. Light cannot travel far before scattering. Matter and radiation remain tightly coupled through electromagnetic interactions, temperatures, and pressures equilibrating continuously. Universe glows like interior of star, every direction brilliant with scattered light, yet nothing visible, because light cannot propagate freely through plasma fog. Imagine immersing yourself within this primordial plasma. Everywhere you look, brilliant orange-white glow surrounds you, photons bouncing between electrons creating uniform illumination. Temperature around 10,000 to 3,000 Kelvin, depending on epoch, hot enough to ionize hydrogen instantly. Plasma density decreases steadily, initially thick as modern liquid water, but thinning exponentially as expansion continues. Acoustic oscillations ripple through plasma, sound waves propagating at half-light speed. These oscillations originated from inflation quantum fluctuations, now manifesting as pressure waves. Dense regions collapse under gravity, compression heats plasma, pressure rebounds pushing outward, rarefaction cools, gravity pulls inward again. This cycle continues hundreds of thousands of years, creating compressions and rarefactions frozen into cosmic microwave background as hot and cold spots. Dark matter plays crucial role, though remaining invisible, interacting only gravitationally. While ordinary matter and radiation oscillate acoustically, dark matter potential wells remain stable, growing steadily deeper through gravitational collapse. This creates characteristic imprint affecting galaxy formation billions of years later. You watch time pass slowly, universe expanding and cooling gradually week after week, millennium after millennium. Around 47,000 years, matter density overtakes radiation density. After this equality, matter's gravitational attraction allows density perturbations growing through gravitational instability. Dark matter halos begin collapsing, building potential wells ordinary matter will later fill. Around 200,000 years, temperature cooled to roughly 4,500 Kelvin, plasma yellow-orange. Every photon travelling through expanding space finds wavelength stretched, energy decreasing, temperature dropping. This cosmological redshift represents cumulative effects of travelling through expanding space-time. Around 380,000 years after beginning, temperature drops to roughly 3,000 Kelvin, critical threshold for recombination. Electrons and nuclei combine into neutral atoms permanently, ending ionization. Temperature just cool enough that electron binding energy exceeds typical photon energies, preventing immediate reionization. Once neutral hydrogen forms, it remains neutral, universe becomes transparent. Thomson scattering ceases abruptly. Free electrons captured into atoms no longer scatter photons. Photons suddenly travel freely without scattering for first time. Those photons last scattered during recombination continue travelling freely for next 13.8 billion years, eventually reaching Earth as cosmic microwave background radiation baby picture of universe at 380,000 years old. Surface of last scattering represents cosmic photosphere. Looking outward in any direction, we see this surface as sphere surrounding us. Measuring temperature fluctuations reveals density variations imprinted during inflation, frozen into recombination pattern, creating hot and cold spots mapping primordial density field. This microwave background represents most perfect blackbody spectrum ever measured, temperature 2.725 Kelvin today after redshifting from original 3000 Kelvin. Recombination produces specific spectral signature. Hydrogen atoms forming release photons at Lyman alpha wavelength, 121.6 nanometers. Electron transitioning from first excited state to ground state. Universe briefly glows with Lyman alpha light before this light redshifts into infrared. Other transitions occur, Balmer series producing visible red light, though most photons concentrate in Lyman alpha. This fluorescence represents universe's visible light swan song before dark ages begin. Once recombination completes around 400,000 years, universe enters cosmic dark ages, epoch without light sources lasting roughly 150 million years until first stars ignite. No stars exist yet, no galaxies, no quasars, just neutral hydrogen gas slowly collapsing into dark matter halos, 21 centimeter emission line weakly radiating as hydrogen atoms undergo hyperfine transition, flipping electron and proton spins. Incredibly faint signal cosmologists hope detecting with radio telescope arrays, probing cosmic dawn, mapping hydrogen distribution during dark ages. You float through dark ages watching nothing visible happen, just expansion continuing, temperature cooling toward 100 Kelvin, then 50 Kelvin, then 20 Kelvin. Complete darkness surrounds you, no light sources anywhere across entire cosmos. Universe exists as vast cold neutral hydrogen cloud, photons from recombination redshifted into infrared and microwave wavelengths, energy densities too low illuminating anything. Cosmic microwave background photons streaming freely, but too redshifted for eyes detecting them even if eyes existed. Density perturbations continue growing gravitationally in dark matter component. Dark matter halos collapsing hierarchically, smallest halos forming, first then merging into larger structures following bottom-up hierarchy. Halos around million solar masses represent first objects massive enough hosting star-forming gas clouds. Ordinary baryonic matter falls into these potential wells, neutral hydrogen and helium streaming inward following dark matter's gravitational pull. Molecular hydrogen forms through trace chemical reactions, proceeding slowly in cold neutral gas. H- ions form when neutral hydrogen atoms capture free electrons remaining from incomplete recombination. These ions then react with neutral hydrogen forming H2 molecules plus free electrons. Though inefficient process requiring multiple steps and rare electrons, sufficient molecular hydrogen accumulates in densest regions, enabling cooling necessary for gravitational collapse proceeding. Gas temperature roughly matches cosmic microwave background temperature initially, around 100 Kelvin at few 100,000 years. But as universe expands and microwave background redshifts and cools, gas temperature follows adiabatically. Without heating sources and with molecular hydrogen radiating away thermal energy through rotational and vibrational transitions, gas cools below 1000 Kelvin in deepest dark matter potential wells approaching 200 Kelvin or lower depending on local conditions. This cooling critical for first star formation. Gas pressure supports clouds against gravitational collapse. Hotter gas means higher pressure requiring stronger gravity for collapse. Cooler gas, lower pressure, allows collapse at lower masses. Molecular hydrogen cooling enables gas collapsing into protostellar clouds massive enough eventually igniting nuclear fusion. Without molecular cooling, gas would remain too hot, pressure preventing collapse even in deepest dark matter wells. Jeans mass, critical mass above which gravitational self-attraction overcomes internal pressure, decreases as temperature drops. Initially Jeans mass around million solar masses when gas temperature thousands Kelvin. As molecular hydrogen cools gas toward few hundred Kelvin, Jeans mass drops to 10,000 solar masses approximately. This allows fragmentation of collapsing clouds into smaller clumps eventually forming individual stars rather than single supermassive object. However, cooling efficiency limited by molecular hydrogen abundance and quantum mechanical selection rules governing radiative transitions. H2 molecule lacks permanent dipole moment being perfectly symmetric, making radiative transitions weak, occurring only through quadrupole and magnetic transitions. This weak cooling prevents temperatures dropping arbitrarily low, establishing floor around 200 Kelvin, below which further cooling very slow. Consequently, first stars form from relatively warm gas compared to modern star formation occurring around 10 Kelvin, making first stars likely more massive than modern stars due to higher Jeans masses. You watch time pass through dark ages patiently, centuries accumulating slowly across cosmic voids. Nothing visible occurs, yet everything preparing quietly beneath. Dark matter halos growing steadily now, ordinary matter falling into potential wells, molecular hydrogen cooling regions, first stars approaching ignition. Around 150 million years after beginning, you witness first light-piercing cosmic darkness. Deep within dark matter, halo containing roughly million solar masses of matter, hydrogen and helium gas collapsed to densities triggering nuclear fusion. Temperature at core climbed past 10 million Kelvin, pressure mounting, hydrogen nuclei fusing into helium through proton-proton chain reactions. First star ignites, population 3 star, massive beyond anything existing in modern universe, perhaps 200 solar masses, maybe 500, possibly exceeding 1,000 solar masses, depending on exact collapse conditions and angular momentum distribution. This first star shines with brilliant blue-white light, surface temperature exceeding 100,000 Kelvin, far hotter than modern sun's 5,800 Kelvin surface. Photons streaming outward carry ultraviolet radiation energetic, enough ionizing surrounding hydrogen gas. Sphere of ionized hydrogen expands outward from star-like cosmic bubble, H2 region growing as photons travel farther, converting neutral hydrogen into ions plus free electrons. This radiative feedback heats nearby gas, raising pressure, potentially preventing additional stars forming nearby, creating negative feedback limiting immediate star formation. You float near this primordial star, watching fusion proceed deep in core. Hydrogen fusing into helium releases energy approximately 0.7% of mass converted to energy via Einstein's mass-energy equivalence. 4 hydrogen nuclei, each roughly 1.008 atomic mass units, combine forming one helium-4 nucleus weighing 4.003 units, missing 0.029 units converted entirely to energy, photons and neutrinos carrying energy outward. Photons take millions of years random walking from core to surface, constantly absorbed and re-emitted by atoms. Neutrinos escape immediately, passing through stellar matter virtually unimpeded, carrying away portion of fusion energy into intergalactic space. Stellar structure maintains hydrostatic equilibrium, gravity pulling inward, balanced by pressure pushing outward from hot, dense core. More massive stars burn hotter and faster, luminosity scaling roughly as mass to fourth power. Star 100 times solar mass shines roughly 100 million times brighter, exhausting fuel proportionally faster. These first massive population 3 stars live perhaps only 2 to 3 million years before exhausting core hydrogen, incredibly brief compared to Sun's 10 billion year main sequence lifetime, or red dwarf stars persisting trillions of years. Composition matters critically for stellar evolution. Modern stars contain metals, astronomers' term for all elements heavier than helium, enabling additional cooling mechanisms and opacity sources affecting stellar structure. Population 3 stars, completely metal-free, composed only primordial hydrogen and helium from Big Bang nucleosynthesis plus trace lithium. Without metals, opacity lower, cores slightly hotter, structures somewhat different, but basic fusion processes similar to modern massive stars, just scaled up. As core hydrogen depletes after few million years, star begins post-main sequence evolution. Core contracts under gravity, temperature rising further. Hydrogen shell surrounding depleted core ignites, fusing into helium and depositing helium onto growing core. Core helium abundance increases until central temperature reaches roughly 100 million Kelvin, hot enough for helium fusion via triple alpha process. 2 helium nuclei collide, forming unstable beryllium-8 nucleus, existing only 10 to the power of minus 16 seconds. If third helium nucleus collides during this brief window, carbon-12 forms. This incredibly sensitive reaction requires precise conditions, but proceeds vigorously once temperature threshold exceeded. Carbon and oxygen, now produced through helium fusion, accumulate in core, while helium burns in shell surrounding it. Star expands tremendously, becoming supergiant, surface cooling despite core heating, luminosity increasing further. For extremely massive population 3 stars, exceeding perhaps 140 solar masses, core temperatures may reach several billion Kelvin, enabling photodisintegration, energetic photons splitting apart nuclei rather than fusing them, leading to pair instability supernova, entire star disrupted, leaving no remnant, all mass returned to space enriched with newly synthesized elements. Stars less massive than pair instability threshold, but still very massive, perhaps 20 to 140 solar masses, continue fusing heavier elements. After carbon-oxygen core forms, contraction raises temperature, enabling carbon fusion around 600 million Kelvin, producing neon and magnesium. Neon fusion follows near 1.2 billion Kelvin. Oxygen fusion, around 1.5 billion Kelvin, creates silicon and sulfur. Finally, silicon fusion, around 2.7 billion Kelvin, produces iron peak elements, fusion chain's endpoint, because iron nuclei most tightly bound, further fusion consuming rather than releasing energy. This entire sequence from helium to iron proceeds rapidly for massive stars, each burning stage briefer than previous. Helium burning lasts roughly 500,000 years, carbon burning perhaps 600 years. neon burning about 1 year, oxygen burning mere 6 months, silicon burning to iron just 1 day. Star develops onion layer structure, iron core surrounded by silicon shell, oxygen shell, carbon shell, helium shell, hydrogen envelope, each layer progressively cooler and less processed, moving outward. Iron core grows through silicon fusion until reaching Chandrasekhar limit, approximately 1.4 solar masses, beyond which electron degeneracy pressure cannot support core against gravity. Core collapses catastrophically in less than 1 second, electrons forced into protons creating neutrons plus neutrinos. Neutron degeneracy pressure finally halting collapse after core compressed to roughly 10 kilometer radius, density exceeding atomic nuclei. Collapse rebounds, shock wave propagates outward through stellar envelope, encountering infalling material, depositing enormous energy through neutrino heating and nuclear reactions, blowing apart entire outer envelope in core collapse, supernova explosion. Supernova brightness rivals entire galaxy temporarily, peak luminosity roughly 10 billion times solar luminosity, visible across hundreds millions of light years. Explosion ejects several solar masses of heavy elements synthesized during star's life, plus additional elements created in supernova explosion itself through rapid neutron capture processes. These elements, carbon, nitrogen, oxygen, silicon, iron, and traces of everything heavier, disperse into surrounding intergalactic medium, enriching primordial gas with first metals, forever changing subsequent star formation by enabling new cooling mechanisms and dust grain formation. Supernova remnant expands outward as shockwave compressing surrounding gas, sweeping up material into expanding shell moving thousands of kilometers per second. This shell glows brilliantly from shock heating and compression, visible for thousands of years as supernova remnant gradually slowing and fading as kinetic energy dissipates. Eventually, remnant merges with surrounding medium, metals mixing thoroughly, seeding future star formation regions with chemical enrichment, enabling planets and eventually life emerging billions of years hence. You watch this first supernova explosion with mixture of awe and melancholy, stars' brief, brilliant life ending in spectacular death, yet death enabling complexity arising later. Without supernovae dispersing heavy elements, universe remains eternally hydrogen and helium, no carbon for organic chemistry, no oxygen for water, no iron for planetary cores or hemoglobin, no rocky planets, no life. Stellar death represents cosmic recycling program, successive generations building upon previous generations' nucleosynthetic achievements. Supernova core collapse leaves behind compact remnant, typically neutron star approximately 10 kilometers radius, containing 1.4 to 2 solar masses compressed to nuclear density around 10 to the power of 17 kilograms per cubic meter. If original star sufficiently massive and core exceeds roughly 3 solar masses, neutron degeneracy pressure fails. Nothing prevents further collapse, object becoming black hole, space-time curvature becoming so extreme that escape velocity exceeds light speed, event horizon forming at Schwarzschild radius approximately 3 kilometers per solar mass. These first black holes, forming from population 3 supernovae, range from perhaps 10 to 100 solar masses, depending on progenitor, star mass, and explosion dynamics. These stellar mass black holes represent seeds potentially growing through accretion and mergers into intermediate mass black holes, thousands to hundreds of thousands solar masses, eventually becoming supermassive black holes, millions to billions solar masses, residing in galaxy centres billions of years later. Though black holes have no hair, according to no-hair theorem, describing black holes entirely by mass, charge, and angular momentum with no other distinguishing features, they certainly manage devouring everything nearby. Cosmic diet modern dieters might envy, growing steadily through patient accretion over cosmic timescales. Alternative black hole formation pathway involves direct collapse of very massive gas clouds in early universe. If conditions prevent fragmentation and star formation, entire cloud collapses directly, forming black hole perhaps 10 to the power of 5 solar masses without forming star first. These direct collapse black holes would provide head start towards supermassive black holes observed in distant quasars less than billion years after Big Bang, where growing black hole from stellar remnant to billion solar masses requires sustained rapid accretion, potentially difficult achieving in available time. Additional population. 3 stars ignite across universe during this epoch from 150 to 400 million years, each metal-free star living briefly and dying dramatically. Some as pair instability supernovae leaving no remnant, others as core collapse supernovae leaving neutron stars or black holes, all enriching intergalactic medium with metals. Star formation rate increases gradually as more dark matter halos reach critical masses, more gas cools sufficiently for collapse, more regions triggering gravitational instability. Universe brightens slowly from growing population of young massive stars, each shining intensely but briefly. Cosmic reionization begins around 400 million years after Big Bang, progressing through next several hundred million years until approximately 1 billion years when universe fully reionized. Those ultraviolet photons from massive population 3 stars and later from first galaxies and quasars stream outward, ionizing neutral hydrogen filling intergalactic space. Photons energetic enough, exceeding hydrogen ionization energy 13.6 electron volts, strip electrons from hydrogen atoms, creating ionized regions expanding around each source, eventually overlapping and merging until entire universe ionized again as it was before recombination. You drift through transitioning universe watching ionization fronts expanding like cosmic soap bubbles, each bubble representing ionized region around ultraviolet source, bubbles growing and connecting, neutral hydrogen islands shrinking and disappearing as reionization completes. This process, critical for structure formation, ionized gas behaves differently than neutral gas, pressure and heating affecting how gas collapses into halos, when stars form, how galaxies assemble, entire subsequent cosmic evolution depending subtly on reionization timing and topology. Gunn-Peterson trough provides observational signature of reionization. Neutral hydrogen efficiently absorbs ultraviolet light at specific wavelengths, corresponding to Lyman series transitions. Before reionization, looking toward distant quasars reveals strong absorption at these wavelengths as light passes through neutral hydrogen. After reionization, absorption drops dramatically because insufficient neutral hydrogen remains. Astronomers observe this transition in quasar spectra at redshifts around 6 to 7, corresponding to approximately 1 billion years after Big Bang, confirming universe reionized by this epoch, though reionization likely began earlier. Possible double reionization scenario suggests initial reionization from massive population 3 stars around 400 million years, followed by recombination and neutral period, then second reionization from first galaxies and quasars few hundred million years later. Evidence remains ambiguous, observations challenging due to Epoch's great distance and faintness. future radio telescopes detecting 21 centimeter emission from neutral hydrogen may map reionization's three-dimensional structure, revealing whether process proceeded smoothly or episodically, with multiple ionization and recombination cycles. First galaxies begin forming around 500 million years after Big Bang, though precise timing depends on definitions. When does collection of stars become galaxy rather than merely stellar cluster? Perhaps require millions of stars gravitationally bound in dark matter halo exceeding 10 to the power of 8 solar masses. By this criterion, first galaxies appear between 500 million and 1 billion years. Dwarf galaxies containing millions to tens of millions of stars, small compared to modern Milky Way's hundreds of billions of stars, but representing significant organizational achievement over scattered population 3 stars. These primordial galaxies assemble through hierarchical mergers, bottom-up structure formation, where small objects form first, then merge into progressively larger systems. Dark matter halos merge when gravitational interactions bring them together. Orbital energy dissipated through dynamical friction, halos spiraling inward and combining. Ordinary matter follows dark matter into merged halos, gas clouds colliding and shock heating, cooling and fragmenting, triggering bursts of star formation in merger-driven starbursts, creating millions of new stars within few million years. You watch 2 small proto-galaxies slowly spiral toward each other over tens of millions of years, orbits decaying through gravitational interactions with surrounding dark matter and tidal forces, eventually colliding in slow-motion cosmic dance lasting hundreds of millions of years. Stars passing through each other harmlessly because stellar spacing so vast that direct stellar collisions, extraordinarily rare even in galaxy mergers. But gas clouds collide directly, shock heating to millions of Kelvin, radiating energy through X-ray emission, cooling and fragmenting into dense clumps collapsing into new stars, merger triggering vigorous starburst, forming thousands of massive blue stars, illuminating merger remnant brilliantly. Stellar populations evolve through these mergers. Population 3 stars, exclusively metal-free, defining population 3. As supernovae enrich gas with metals, subsequent star generations contain trace metals, defining population 2 stars, old metal poor stars with heavy element abundances roughly 0.1 to 1% solar levels. Eventually continued enrichment produces population 1 stars like Sun, young metal-rich stars with approximately solar metallicity or higher, located primarily in galaxy disks, where ongoing star formation continues enriching gas progressively. Galaxy morphology develops through mergers and gas accretion. Early galaxies, mostly irregular and disturbed, lacking well-defined structures, undergoing frequent mergers preventing settled configurations. As mergers become less frequent and gas accretion slows, galaxies settle into stable configurations, rotation-supported disks forming for gas-rich galaxies experiencing quiescent accretion, pressure-supported ellipticals forming from gas-poor major mergers scrambling ordered rotation into random motions. Spiral structure develops in rotating disks through density wave mechanism, spiral arms representing regions of enhanced density moving around disk like traffic jams, compressing gas and triggering star formation, illuminating spiral arms with young blue stars. Milky Way assembly begins during this epoch, around 1 to 5 billion years after Big Bang, through mergers of numerous smaller galaxies gradually building mass toward modern configuration containing roughly 100 billion stars total within dark matter halo approximately trillion solar masses. Stellar archaeology, studying old stars in Milky Way's halo and thick disk, reveals ancient merger history. Distinct stellar populations with different ages and chemical compositions, indicating assimilation of satellite galaxies over billions of years. Major merger around 10 billion years ago, approximately 3 to 4 billion years after Big Bang, brought substantial mass into proto-Milky Way, event called Gaia-Enceladus merger after European Space Agency's Gaia spacecraft revealed its signature in stellar motions and compositions. This merger contributed billions of stars to Milky Way's halo and thick disk, significantly affecting galaxy's structure and evolution, possibly thickening disk and stirring up existing stellar populations through dynamical heating during gravitational interactions. Milky Way's central supermassive black hole, Sagittarius A star, grows during this period through gas accretion and potentially black hole mergers, reaching approximately 4 million solar masses by present day. The black hole's exact formation mechanism remains uncertain, possibly beginning as direct collapse black hole or stellar mass black hole growing through sustained accretion, possibly multiple seed black holes merging and accreting. Supermassive black holes commonly reside in massive galaxy centers, correlation between black hole mass and galaxy bulge mass, suggesting co-evolution between black holes and host galaxies through feedback mechanisms regulating both black hole growth and star formation. Active galactic nuclei and quasars represent supermassive black holes accreting matter rapidly, gas spiraling inward through accretion disk heated to millions of Kelvin by friction and gravitational compression, radiating across electromagnetic spectrum from radio through gamma rays. Most luminous quasars outshine entire galaxies from central regions smaller than solar system. Accretion power converting roughly 10% of infalling matter's rest mass energy to radiation compared to fusion's 0.7% efficiency, making black hole accretion most efficient energy generation mechanism in universe aside from matter-antimatter annihilation. Quasar winds and jets driven by accretion provide feedback regulating galaxy evolution. Powerful outflows blow gas out of galaxy centers, temporarily suppressing star formation by removing raw material, heating remaining gas, preventing immediate collapse, potentially quenching star formation and transforming blue star-forming galaxies into red quiescent galaxies. Jets launched perpendicular to accretion disk along black hole rotation axis by complex magneto-hydrodynamic processes involving magnetic fields threading accretion disk and ergosphere, shoot relativistic particles into intergalactic space at velocities approaching light speed, depositing enormous energy into surroundings inflating giant radio lobes visible millions of light years across. You float above, forming Milky Way, watching it grow through mergers and accretion across billions of years, disk gradually assembling, spiral arms developing, central bulge forming from early mergers and violent relaxation processes, stellar halo populating with stars from disrupted satellites, thin disk establishing through continued gas accretion and in situ star formation. Milky Way slowly becoming recognizable spiral galaxy destined hosting solar system and eventually life on small rocky planet orbiting average yellow star in quiet outer disk region. Star formation rates peak between 2 to 3 billion years after Big Bang cosmic star formation rate density roughly 10 times higher than present day, universe blazing with young galaxies vigorously forming stars consuming available gas rapidly. This cosmic noon represents universe's most productive epoch for converting gas into stars, building majority of stellar mass existing in present-day galaxies. After cosmic noon, star formation gradually declines as gas supplies deplete. Quasar feedback suppresses formation in massive galaxies. Dark energy accelerates expansion, reducing gas densities. Star formation settling into quiescent maintenance mode, forming new stars at reduced rates. Intergalactic medium enriched progressively through stellar winds and supernovae ejecting metals into surroundings. Initially pure primordial composition, intergalactic gas gradually contaminated with trace metals, abundance increasing logarithmically over cosmic time as successive stellar generations synthesize and eject heavier elements. By redshift 6, approximately 1 billion years after Big Bang, intergalactic metallicity reaches roughly 0.001 solar, sufficient affecting subsequent structure formation by enabling additional cooling mechanisms through metal line radiation, increasing cooling efficiency, lowering Jeans mass, allowing smaller structures forming. Cosmic chemical evolution follows predictable patterns as different elements produced in different environments. Alpha elements like oxygen, magnesium, silicon, calcium primarily produced in massive short-lived stars ending as core collapse supernovae, ratios enhancing early in galaxies' histories. Iron peak elements primarily produced in Type 1 as supernovae. White dwarf stars accreting matter from binary companions until reaching Chandrasekhar limit and detonating in thermonuclear explosions. These longer-lived progenitor systems delaying peak iron production, creating time-dependent abundance patterns encoding galaxies' star formation histories in present-day stellar compositions. Heavy elements beyond iron produced through neutron capture processes, slow neutron capture called S process, occurring in asymptotic giant branch stars during late stellar evolution, rapid neutron capture called R process, occurring in extreme neutron-rich environments, possibly neutron star mergers or special types of supernova, creating heaviest elements like gold, platinum, uranium through rapid successive neutron captures before beta decay proceeds. Recent gravitational wave detection of neutron star merger directly observed R-process nucleosynthesis through kilonova transient emission, confirming merger sites as major R-process production locations. Dust grains form in stellar atmospheres and supernova ejecta, tiny solid particles typically 0.01 to 1 micrometer diameter composed of silicates, carbon or iron depending on formation environment. These microscopic particles profoundly affect subsequent star formation by providing surfaces catalyzing molecular hydrogen formation, shielding molecules from dissociating ultraviolet radiation, absorbing and scattering starlight, altering galaxy colors and dimming distant objects, re-radiating absorbed energy as infrared emission detectable in dusty galaxies' spectral energy distributions. Dust abundance increases with metallicity. Modern universe roughly 1% of metals locked in dust grains. Early low metallicity universe containing less dust, affecting how primordial star formation proceeds compared to modern dusty star-forming regions. Cosmic web structure becomes increasingly apparent as overdense regions collapse, forming galaxy clusters connected by filaments, while underdense voids expand and empty. Density perturbations from inflation seeded linear theory predictions, perturbations growing proportional to scale factor during matter domination, transitioning to non-linear regime when density contrasts exceed unity, requiring numerical simulations predicting complex web structure observed in galaxy redshift surveys mapping three-dimensional large-scale structure revealing clusters, filaments, walls, voids, arranged in cosmic web spanning hundreds of millions of light years. Galaxy clusters represent densest regions in cosmic web, containing hundreds to thousands of galaxies within regions several million light years across, total masses reaching 10 to the power of 14 to 10 to the power of 15 solar masses dominated by dark matter. Clusters form through hierarchical mergers over billions of years. Gravitational attraction drawing galaxies together, orbital velocities reaching thousands of kilometers per second, hot intracluster gas heated to tens of millions of Kelvin through shock heating, emitting copious X-rays observable with telescopes revealing cluster masses and dynamics. You float through forming galaxy cluster, watching member galaxies interact gravitationally, tidal forces stripping gas from galaxies passing through hot medium, ram pressure stripping gas from disks as galaxies plough through plasma, gas remaining behind while stars continue unaffected, transforming gas-rich spirals into gas-poor ellipticals through environmental processes occurring only in dense cluster environments where interactions frequent and intracluster medium substantial. Cosmic filaments connect clusters, forming superhighways along which galaxies stream, matter flowing along density. Gradients from voids into filaments and clusters. Filaments extend tens to hundreds of millions of light years, width few million light years, containing most universes' baryonic matter in diffuse medium and galaxies strung along filaments. Gas temperatures along filaments reach millions of Kelvin, shock-heated by compression, emitting faint X-rays detectable in spectral lines along quasar sightlines. Cosmic voids between filaments represent underdense regions expanded through gravitational evacuation as matter flows toward overdensities. Typical void diameter approximately 100 million light years, matter density 10 to 20% of cosmic mean, few galaxies residing in void interiors. Void galaxies differ from average, typically lower mass, lower metallicity, higher gas fractions, less evolved, reflecting environments lacking frequent interactions, driving rapid evolution in denser regions. Baryon, acoustic oscillations imprinted during recombination persist as subtle clustering pattern in galaxy distribution, characteristic scale roughly 150 megaparsecs. Galaxies preferentially separated by this distance, creating excess correlation, standard ruler measuring cosmic expansion history and testing dark energy models. Measurements at multiple redshifts constrain dark energy equation of state determining whether dark energy density constant or evolving. Key question for fundamental physics. Gravitational lensing becomes observable as light from distant galaxies passes near massive foreground clusters, space-time curvature, bending light paths creating multiple images, arcs, and Einstein rings around massive clusters. Strong lensing produces dramatic distortions when alignment particularly favorable, background galaxy image stretched into arc wrapping around cluster center, occasionally forming complete Einstein ring when alignment perfect. Weak lensing produces subtle shape distortions in background galaxies, statistically detectable, revealing total matter distribution, including dark matter independent of luminous tracers. Clusters act as cosmic telescopes, magnifying distant background galaxies through gravitational lensing, enabling observations of extremely distant and faint galaxies otherwise undetectable with current telescopes. Some most distant galaxies known detected through cluster lensing, magnifying their light by factors 10 to 100, bringing faint objects into detectability. James Webb Space Telescope exploits cluster lensing, observing behind massive clusters, finding galaxies existing when universe only few 100 million years old, glimpsing universe's infancy, directly testing galaxy formation theories against observations. Dark matter distribution mapping through gravitational lensing reveals dark matter halos surrounding galaxies and clusters, confirming theoretical predictions about dark matter's role structuring universe. Lensing measurements provide direct evidence that dark matter's mass distribution extends well beyond visible galaxies. Dark matter halos approximately 10 times more massive than enclosed luminous matter. Mass-to-light ratios increasing with system size from galaxies to clusters consistent with hierarchical structure formation models where dark matter dominates gravitational dynamics throughout cosmic history. Time passes, universe ages from 1 billion to 5 billion years. After Big Bang, galaxies continue assembling and evolving, Milky Way reaching roughly half its present-day stellar mass by 5 billion years, post-Big Bang, disk establishing, spiral structure developing, bar possibly forming, and reforming through disk instabilities and satellite interactions, stellar populations diversifying as metallicity increases through continued star formation and chemical enrichment. Other galaxies follow similar evolutionary tracks, massive ellipticals mostly complete by this epoch through major mergers, spiral galaxies continuing disk growth through minor mergers, and gas accretion sustaining star formation. Galactic ecosystems develop feedback loops regulating star formation, stellar winds, and supernovae injecting energy and momentum into interstellar medium, creating turbulence and driving galactic-scale outflows, removing gas from galaxies temporarily or permanently depending on galaxy mass and outflow velocities, quenching star formation until gas cools and reaccretes, or new gas falls in from intergalactic medium replenishing supplies. Equilibrium models balance gas accretion rates with star formation rates and outflow rates, predicting galaxy stellar masses and star formation rates matching observations across cosmic time, validating feedback-regulated galaxy evolution paradigm. Black hole galaxy co-evolution proceeds through mutual feedback, black holes growing through accretion, simultaneously producing powerful winds, and jets regulating gas supply and star formation, establishing observed correlations between black hole masses and galaxy bulge properties, suggesting coupled evolution. Precisely how black holes and galaxies co-evolve remains active research area. Simulations, including black hole feedback, reproduce observed galaxy properties better than simulations. Omitting feedback, confirming feedback's importance, though detailed physical mechanisms and efficiency parameters remain uncertain, requiring further theoretical and observational work. You watch galaxy after galaxy evolving across billions of years, some merging violently, triggering intense starbursts, forming millions of stars within 10 million years before gas depletion and feedback quenches, formation leaving gas-poor elliptical galaxy, others growing steadily through gentle gas accretion, maintaining continuous star formation at moderate rates, building disk galaxies with ongoing formation and chemical evolution. Diversity of evolutionary pathways producing observed variety of galaxy types from giant ellipticals to dwarf irregulars to spirals and lenticulars populating galaxy morphology sequence. Eons pass, universe ages toward 9.2 billion years after Big Bang specific moment and location where solar system will form approaches. In outer region of Milky Way's disk, approximately 26,000 light-years from galactic center, molecular cloud begins collapsing, local density enhancement triggering gravitational instability, cloud fragment contracting under self-gravity, rotation increasing as conservation of angular momentum requires, temperature rising as gravitational potential energy converts to thermal energy through virial theorem relating gravitational and kinetic energies in bound systems. Molecular cloud mass approximately few thousand solar masses, size several light years across, temperature roughly 10 Kelvin, maintained by balance between cosmic ray heating and molecular line cooling, primarily through carbon monoxide rotational transitions radiating infrared photons carrying thermal energy away, allowing gas remaining cool enough for gravitational collapse proceeding. Cloud composition approximately 70% hydrogen, 28% helium, 2% heavier elements by mass, metallicity near solar value, approximately 2% heavy elements indicating significant prior stellar generations enriching gas through supernovae and stellar winds. Gene's mass in molecular cloud approximately 1 solar mass given temperature and density. Cloud fragments into numerous collapsing cores, each forming individual star or stellar system. Clustered star formation producing stellar nursery containing hundreds of young stars rather than isolated star formation. Our protosun collapses from one such core, mass roughly 1 solar mass, making it typical middle-aged yellow dwarf destined living approximately 10 billion years total, currently halfway through main sequence lifetime, having already lived 4.6 billion years since formation. Collapse proceeds inside out, inner regions collapsing faster, reaching higher densities first, protostar forming at center, accreting infalling material from surrounding envelope accretion, rate initially high, perhaps 10 to the power of -5 solar masses per year, gradually declining as envelope depletes. Accretion shock heating infalling gas as material lands on protostar surface. Protostellar luminosity, mostly from gravitational potential energy release rather than fusion, initially because core not yet hot enough for sustained hydrogen fusion requiring 10 million Kelvin core temperatures. Protoplanetary disk forms from angular momentum conservation. Infalling material cannot collapse directly onto protostar due to rotation. Instead settles into disk orbiting protostar in plane perpendicular to rotation axis. Disk thin compared to radius, approximately 100 astronomical units across, but only few astronomical units thick initially. Disk heated by viscous dissipation, converting orbital energy to heat through turbulence and magnetic fields, generating friction within disk material. Disk temperature decreases with distance from protostar, hot inner regions exceeding 1000 Kelvin, where only refractory materials like silicates condense. Cooler outer regions around 100 Kelvin, where volatile ices condense forming frost line, beyond which water ice stable roughly 3 astronomical units from protostar. Dust grains within disk begin growing through coagulation, microscopic particles colliding and sticking through electrostatic and van der Waals forces, grains growing from submicron to millimeter sizes over thousands of years, larger grains settling toward disk midplane, concentrating solid material, increasing collision rates, accelerating growth, grains growing through pairwise collisions until reaching meter sizes, where growth stalls temporarily due to fragmentation from high-velocity collisions and radial drift causing meter-sized boulders spiraling inward towards star within centuries, losing angular momentum through gas drag faster than growing further. Planetesimal formation represents critical but uncertain step bridging meter-sized boulders to kilometer-sized planetesimals, possibly occurring through streaming instability where local concentrations of pebbles gravitationally collapse directly into planetesimals bypassing problematic meter-size barrier, or through turbulent concentration mechanisms collecting particles into dense clumps reaching gravitational instability threshold. Somehow meter-sized obstacles overcome, allowing planetesimals forming, representing building blocks for subsequent planet assembly. Once planetesimals reach kilometre sizes, gravitational focusing enhances collision rates dramatically. Larger planetesimals attracting smaller ones through gravity, increasing collision cross-section beyond geometric cross-section. Runaway growth ensues where largest planetesimals grow fastest, creating oligarchs dominating local feeding zones, tens of Moon to Mars mass planetary embryos forming within a few astronomical units, while hundreds of Ceres to Pluto mass objects form in outer solar system, where lower densities and longer orbital periods slow formation compared to inner regions. Inner solar system embryos undergo giant impacts phase, final assembly, through mutual collisions between planetary embryos occurring over tens to hundreds million years, collisions between moon mass to Mars, mass objects determining final planet masses and orbital configurations, stochastic nature of giant impacts explaining diversity among terrestrial planets despite similar formation environment, collisions violent enough melting planetary interiors, creating magma oceans taking millions of years cooling and differentiating into core mantle crust structure. Moon forms through giant impact approximately 50 million years after solar system formation. Mars-sized object called Theia collides with proto-Earth at oblique angle. Impact vaporizes and liquefies impactor and portions of Earth's mantle. Debris thrown into orbit around Earth coalescing into Moon within centuries. Impact partially mixing impactor material with Earth mantle, explaining lunar composition's similarity to Earth mantle, though depletion of volatiles and iron indicating Moon formed from impact vaporized silicate material rather than intact impactor core. Jupiter forms beyond frost line where ices condense, supplementing rock content. Planet core, reaching approximately 10 Earth masses, triggers rapid gas accretion from protoplanetary disk, runaway gas accretion, adding hundreds of Earth masses of hydrogen and helium within few million years before disk dissipates, halting accretion. Jupiter reaching approximately 318 Earth masses, mostly hydrogen and helium, with rocky icy core, few to several tens, Earth masses, depending on exact formation mechanism, whether core accretion or gravitational instability models preferred. Saturn forms, similarly, though reaching lower final mass, approximately 95 Earth masses, indicating either slower formation, allowing more time for disk dissipation before runaway gas accretion completed, or less favourable location with lower gas density, reducing accretion efficiency. Exact reasons remain debated. Neptune and Uranus masses approximately 15 to 17 Earth masses, suggesting gas accretion less efficient, possibly due to longer formation timescales at larger orbital distances or disk dissipation before substantial gas envelopes accreted. Ice giants containing proportionally more rock and ice compared to hydrogen-helium than gas giants Jupiter and Saturn. Planetary migration occurs during and after formation as planets exchange angular momentum with disk and each other, Jupiter possibly migrating inward, then outward in grand tack scenario, Neptune migrating outward, scattering planetesimals producing scattered disk and Oort cloud, migration reshaping original configurations substantially. Late heavy bombardment approximately 4.1 to 3.8 billion years ago represents final major bombardment phase when inner solar system experienced increased impacts possibly triggered by giant planet migration, destabilizing asteroid belt, cratering records showing spike in impact rates, impacts delivering water and organics to inner planets contributing to Earth's oceans and prebiotic chemistry. You watch solar systems settling into stable configuration after turbulent first several 100 million years, planets achieving nearly circular orbits. Asteroid belt representing leftover planetesimals prevented forming planets by Jupiter's stirring. Kuiper belt preserving primordial icy planetesimals. Comets residing in distant Oort cloud. Solar system architecture reflecting complex formation history preserved across 4.6 billion years now. Approximately 10.4 billion years after Big Bang, roughly 4 billion years ago in Earth's geological timeline, young planet Earth orbits middle-aged yellow star at comfortable distance, receiving moderate warmth, liquid water, stable on surface, across most latitudes. Atmosphere-composed nitrogen, carbon dioxide, water vapour, trace gases, no free oxygen yet because photosynthesis hasn't evolved. Reducing atmosphere unable, supporting complex life but perfect for prebiotic chemistry. Assembling life's molecular building blocks through lightning, ultraviolet radiation, volcanic heat, driving chemical reactions, producing amino acids, nucleotides, sugars, lipids, organic molecules accumulating in warm, shallow ponds, tidal pools, hydrothermal vents, anywhere liquid water meets energy gradients. You float above early Earth, watching primitive oceans covering most surface, volcanic islands smoking, continents small and barren, atmosphere hazy orange-brown from methane and organic hazes, no green anywhere because plants don't exist yet, lifeless but not sterile. Chemistry happening everywhere, water touches minerals and energy. Self-organizing molecular systems emerging through trial and error across millions of years, countless failed experiments discarded, rare successful combinations persisting and replicating, natural selection beginning at molecular level before life properly defined. Hydrothermal vents deep on ocean floor provide ideal environments for life's origins. Hot, mineral-rich water streaming from Earth's interior, meeting cold ocean water, creating chemical gradients, alkaline vents forming microscopic pores in mineral precipitates, providing natural compartments, concentrating organic molecules, pH gradients across pore walls, driving primitive metabolism, analogous to modern cells' proton gradients, powering ATP synthesis. Mineral surfaces catalyzing reactions, assembling complex molecules from simple precursors, iron-sulfur clusters similar to modern enzyme, active sites forming spontaneously facilitating electron transfer reactions fundamental to metabolism. RNA world hypothesis suggests first replicating molecules were RNA rather than DNA, ribonucleic acid, capable both storing genetic information like DNA and catalyzing chemical reactions like proteins, dual functionality allowing RNA systems potentially self-replicating and evolving without requiring proteins initially. RNA polymerase ribozymes, copying RNA sequences with modest fidelity sufficient for evolution. Proceeding through variation and selection, RNA world eventually replaced by DNA-RNA protein world, offering greater stability and functionality through specialized molecules handling information storage, catalysis, structural roles separately. First cells emerge perhaps 3.8 to 4 billion years ago, exact timing uncertain due to limited geological record from Earth's earliest eons, earliest potential fossils controversial, whether truly biological or merely mineral structures mimicking cellular morphology. Isotopic evidence suggesting biological carbon fractionation by 3.8 billion years ago indicates metabolism already established, implying life originated earlier, possibly within first several 100 million years after Earth's formation, rapid emergence suggesting either life's origins relatively easy given proper conditions, or alternatively that life arrived from space via panspermia, though this merely displaces origins question to elsewhere. Last universal common ancestor, LUCA, represents most recent organism from which all modern life descended, existed perhaps 3.5 to 3.8 billion years ago, judging from molecular phylogenetics comparing genes across all domains of life. LUCA already sophisticated with DNA, RNA, proteins, ribosomes, membrane-bound cells, metabolic pathways including electron transport chains, and ATP synthesis, suggesting substantial evolution occurred between first replicating molecules and LUCA. Early evolutionary history lost to time without fossil record preserving molecular details. LUCA's descendants diversifying into three domains: bacteria, archaea, eukaryota, splitting early in life's history, though exact branching order debated. For next 2 billion years, life remains exclusively microbial, bacteria and archaea, diversifying into countless species occupying every available niche, from hot springs to frozen wastes, deep ocean trenches to atmospheric aerosols, metabolic innovations arising, including oxygenic photosynthesis by cyanobacteria around 2.7 billion years ago, splitting water molecules using sunlight to extract hydrogen for reducing carbon dioxide, releasing molecular oxygen as waste product, oxygen initially absorbed by dissolved iron in oceans precipitating as rust forming banded iron formations, eventually oxygen accumulating in atmosphere, transforming Earth's surface chemistry fundamentally. Great oxidation event around 2.4 billion years ago when atmospheric oxygen levels rose dramatically, mass extinction of anaerobic organisms intolerant of oxygen, survivors retreating to anoxic refuges or evolving detoxification mechanisms, opening ecological opportunities for aerobic respiration, extracting far more energy from food molecules than anaerobic fermentation. Eukaryotic cells emerge through endosymbiosis, large archaeal host cell-engulfing aerobic bacteria becoming mitochondria, providing efficient ATP production through oxidative phosphorylation, separate endosymbiotic event, incorporating cyanobacteria becoming chloroplasts in plant lineage, eukaryotes possessing membrane-bound nucleus, separating DNA from cytoplasm, complex internal membranes organizing cellular functions, cytoskeleton enabling cell shape changes and movement, sexual reproduction shuffling genetic material, accelerating evolution, eukaryotes remaining single-celled for billion years before multicellularity evolves multiple times independently in different lineages, including animals, plants, fungi, seaweeds. Multicellular animals appear suddenly in fossil record during Cambrian explosion approximately 540 million years ago, though molecular clocks suggest animal origins perhaps 100 million years earlier. Ediacaran biota preceding Cambrian, representing early animal experiments, with different body plans mostly extinct without modern descendants. Cambrian explosion seeing rapid diversification of animal phyla within 10 to 20 million years, relatively brief interval producing most major animal body plans persisting today. Explanations debated including ecological factors like predator-prey arms races, developmental innovations like Hox genes controlling body patterning, environmental changes like oxygenation supporting larger, more complex organisms. You watch life's creativity expressed through countless forms over hundreds of millions of years. Trilobites with compound eyes scuttling across Cambrian seafloors, filtering sediments, ammonites spiralling through ancient seas, propelling with siphon jets, Early plants colonizing barren continents, transforming lifeless rocks into green landscapes through photosynthesis and soil formation. Insects taking flight in carboniferous forests, becoming first animals mastering air, fish developing lungs crawling onto land, becoming amphibians, reptiles, evolving waterproof eggs, conquering dry environments dominating Mesozoic, dinosaurs ruling terrestrial ecosystems for 160 million years before asteroid impact 66 million years ago, ending their reign. Except for bird descendants continuing their lineage, mammals radiating into ecological niches vacated by dinosaur extinction, diversifying into thousands of species, primates emerging in trees, developing grasping hands and forward-facing eyes, eventually human lineage appearing several million years ago in Africa, consciousness arising, allowing universe contemplating itself, intelligence reflecting upon cosmos that created it through 13.8 billion years of cosmic evolution, brief flowering of awareness on one small planet orbiting average star in outer regions of typical spiral galaxy. Present day, 13.8 billion years after Big Bang, universe continues expanding. Accelerating expansion driven by dark energy discovered late 1990s through distant supernova observations, showing universe's expansion rate increasing contrary to expectations of gravitational deceleration, dark energy constituting roughly 68% of universe's total energy density, dark matter approximately 27%, ordinary baryonic matter merely 5%, vast majority of universe's contents invisible and mysterious, defying direct detection, dark energy's nature unknown, whether cosmological constant representing vacuum energy, density, or dynamical field evolving, with time-like quintessence models suggest fundamental physics question with profound implications for universe's ultimate fate, determined by dark energy's equation of state parameter. Galaxies continue evolving through present epoch, star formation declining gradually from cosmic noon peak billions of years ago, gas supplies depleting through star formation, exhausting molecular clouds, fewer dense clouds collapsing into new stars, stellar populations aging as massive short-lived blue stars die, leaving behind long-lived red dwarfs and stellar remnants, white dwarfs, neutron stars, black holes, galaxies, integrated colours shifting from blue, indicating young hot star populations, to red indicating old cool star populations, spiral galaxies gradually becoming redder as star formation slows, though maintaining some formation in spiral arms, morphological transformations through mergers, converting gas-rich spirals into gas-poor ellipticals through tidal interactions and ram pressure stripping, removing gas, universe growing darker and redder as cosmic time passes, star formation era representing brief bright interval in much longer cosmic history stretching trillions of years into future darkness. Milky Way's future evolution includes inevitable collision with Andromeda galaxy approximately 4 billion years hence, currently approaching at 110 kilometers per second, closing distance 2.5 million light-years separating galaxies. Presently, gravitational attraction dominating over cosmic expansion within local group, allowing galaxies falling toward each other, collision occurring as slow-motion merger lasting several billion years rather than instantaneous crash, galactic disks interpenetrating, passing through each other multiple times, exchanging stars and gas before gravitational interactions dissipate orbital energy, allowing galaxies settling into single elliptical galaxy. Astronomers nicknamed Milkomeda, combining Milky Way and Andromeda names, Despite dramatic restructuring, individual stellar collisions remain extremely rare due to vast spacing between stars averaging several light years. Separation, solar system likely surviving merger intact, though possibly relocated to different galactic region through gravitational scattering. Sun remaining stable main sequence star throughout merger having approximately 5 billion years hydrogen fuel remaining in core before red giant phase begins. Sun's future evolution proceeds predictably as middle-aged yellow dwarf star currently halfway through 10 billion year main sequence lifetime, core hydrogen fusion continuing steadily converting hydrogen into helium, gradually enriching helium core, luminosity slowly increasing roughly 10% per billion years as core contraction increases central temperature and fusion rate. Earth receiving incrementally more solar radiation, potentially causing runaway greenhouse effect evaporating oceans within billion years, rendering Earth uninhabitable for complex life, though microbial extremophiles possibly surviving longer in subsurface environments. Eventually, after 5 billion more years, core hydrogen exhausted triggering red giant phase, Sun expanding to perhaps Earth's orbit radius, or beyond engulfing Mercury and Venus, certainly, Earth possibly surviving at greater distance, heated to molten state. Sun shedding outer layers through stellar winds, eventually exposing hot white dwarf core, remnant cooling indefinitely. Local group containing Milky Way, Andromeda, Triangulum galaxies, plus dozens of dwarf satellites, will eventually merge into single massive elliptical galaxy over next tens of billions of years. Dark energies accelerating expansion, preventing gravitationally unbound galaxies beyond local group from ever reaching us. Despite vast numbers, visible currently, cosmic event horizons forming around gravitationally bound structures, isolating them from rest of universe. Eventually only local group merger, remnant visible to any observers within it, hypothetically present. Rest of universe receding beyond observable horizon, carried by expansion faster than light speed, allowed travel closing cosmic curtain leaving island. Universe alone in infinite expanding darkness. Last photons from distant galaxies arriving redshifted into undetectability. Night sky gradually darkening as galaxies disappear beyond horizon one by one. Star formation gradually ceases as universe ages through tens, then hundreds of trillions of years. Molecular gas supplies exhausted through star formation, converting available hydrogen helium into stars and stellar remnants. Remaining diffuse gas, heated by shocks and dark energy expansion, preventing gravitational collapse below Jeans mass threshold. Star-forming molecular clouds becoming increasingly rare as existing clouds consumed without replenishment from intergalactic medium gas falling into potential wells. Last stars forming perhaps 100 trillion years hence, depending on assumptions about dwarf galaxy mergers, collecting remaining gas and gas recycling through stellar winds and supernova, universe transitioning from stelliferous era dominated by shining stars to degenerate era dominated by stellar remnants, white dwarfs, neutron stars, black holes, brown dwarfs, failed stars, never achieving fusion, planets wandering freely, ejected from dying stellar systems, cold, dead objects drifting through expanding space, growing increasingly isolated, darkness punctuated only by occasional collisions or matter falling into black holes, releasing gravitational energy as brief flashes before silence returns. Red dwarfs represent longest-lived true stars, lowest mass stars capable sustained hydrogen fusion, approximately 0.08 to 0.5 solar masses, fusing hydrogen incredibly slowly due to low core temperatures reaching only several million Kelvin compared to Sun's 15 million Kelvin. main sequence lifetimes measured in trillions of years, extending far beyond current universe age. Most massive red dwarfs living perhaps 10 trillion years, least massive potentially exceeding 20 trillion years, fully convective interiors mixing, bringing fresh hydrogen fuel from surface to core, allowing complete hydrogen consumption. Unlike more massive stars, wasting most hydrogen in non-convective envelopes, never reaching fusion core, red dwarfs eventually exhausting fuel, becoming helium white dwarfs, after enormously long main sequence lifetimes representing stars' final sustainable light sources, last red dwarf deaths marking final natural starlight in universe aside from rare accretion events and stellar collisions providing transient illumination. You drift forward through cosmic time, watching trillions of years passing like moments, galaxies dissolving through stellar evaporation as gravitational three-body interactions occasionally impart velocities exceeding escape velocity. Stars flung into intergalactic space one by one over incomprehensible timescales measured in quadrillions of years. Galaxy remnants becoming increasingly diffuse as central regions deplete while outlying regions expand. Stellar orbits gradually decaying through gravitational radiation emission as binary star systems radiate gravitational waves carrying away orbital energy, causing orbits slowly shrinking through in-spiral lasting trillion-year timescales. Typically, process extraordinarily slow for typical stellar separations, but inexorable given sufficient time. Eventually most stars either ejected into intergalactic space through n-body scattering or collapsed into central supermassive black holes through dynamical relaxation processes gradually funneling stars inward toward galactic centers. Around 10 to the power of 15 years, approximately 1 quadrillion years hence, universe enters degenerate era proper, as astronomers classify future epochs. All conventional fusion-powered stars dead and cold, universe populated entirely by stellar remnants and planets and substellar objects, white dwarfs cooling toward blackness, neutron stars frozen solid, brown dwarfs cold and dark, black holes silently accreting occasional matter, darkness nearly absolute and complete except for rare transient events punctuating eternal night, occasional white dwarf collisions producing brief type 1. A supernovae flashing then fading, neutron stars colliding, creating kilonovae, illuminating small regions briefly before darkness returns, matter falling into black holes, producing accretion radiation flickering weakly. These events increasingly rare as matter becomes increasingly dilute through cosmic expansion and stellar evaporation, leaving vast empty spaces, light years, then tens of light years, then hundreds of light years between isolated remnants drifting alone. White dwarfs by this epoch cool to temperatures barely above cosmic microwave background radiation temperature, themselves cooled through expansion redshift to perhaps millikelvin levels. White dwarfs radiating last thermal energy at wavelengths stretched to meters or kilometers. Essentially invisible infrared sources barely warmer than surrounding space, interiors completely crystallized into ordered lattices of carbon-oxygen nuclei or oxygen-neon-magnesium for more massive white dwarf progenitors, electrons forming degenerate Fermi, C filling lowest available quantum states, unable to radiate further energy without external input, white dwarfs achieving equilibrium temperature, matching background, remaining stable, indefinitely barring external perturbation, black dwarfs in practice, if not theory given universe, insufficiently aged for complete cooling, yet but approaching this state asymptotically through quadrillions of years. Proton decay if occurs according to some grand unified theories, begins noticeably affecting matter around 10 to the power of 34 years, though lower limits from Super Kamiokande and other experiments suggest proton lifetime exceeds 10 to the power of 34 years for most decay modes. Grand unified theories typically predicting proton decay through barrier number violating processes where proton transforms into positron plus neutral pion, decaying immediately into gamma-ray photons, alternative decay modes possible. Depending on specific theory producing different particles, proton decay, if occurring, would gradually dissolve all normal matter including white dwarfs, neutron stars, planets, asteroids, dust gas, everything composed of protons and neutrons, white dwarfs slowly evaporating as constituent protons decay one by one. Over googles of years, mass, decreasing infinitesimally slowly, luminosity from decay energy briefly exceeding cooling. Luminosity before that too fades, eventually leaving only electrons, positrons, and radiation, as all baryonic matter disappears completely, though proton decay remains experimentally unconfirmed, theoretical possibility, depending on physics beyond standard model not yet discovered. Without proton decay, alternative scenario unfolds, where white dwarfs and neutron stars remain indefinitely stable, gradually crystallizing as temperatures approach absolute zero asymptotically. White dwarf interiors crystallizing into perfect lattices of carbon-oxygen nuclei surrounded by degenerate electron gas, crystallization releasing small amount of gravitational binding energy as lattice forms providing temporary luminosity, pulse before final cooling, phase transition from liquid to solid occurring over millions of years as crystallization front propagates from core outward through white dwarf interior, eventually white dwarfs becoming perfectly dark, perfect crystals floating through space forever, largest diamonds imaginable, spanning thousands of kilometers, composed of crystallized carbon nuclei, neutron stars similarly freezing into solid nuclear matter lattices, neutron superfluidity and proton superconductivity appearing in cores, creating frictionless flow and perfect conductivity. Eventually neutron stars becoming cold, inert nuclear crystals persisting eternally unless disturbed by rare collisions or tidal disruption passing near black holes. Black holes dominate matter budget in far future universe after stellar remnants evaporated or decayed. Supermassive black holes in former galaxy centers containing millions to billions of solar masses silently waiting. Stellar mass black holes formed from massive star collapse ranging tens to hundreds. Solar masses scattered through space, possibly intermediate mass black holes, thousands to hundreds of thousands solar masses. If such objects exist formed through runaway mergers or direct collapse, black holes appearing eternal, timeless, unchanging from outside perspective, but actually evaporating through Hawking radiation quantum mechanical effect, causing black holes radiating thermal spectrum from event horizons, though emission rate extraordinarily slow for macroscopic black holes, radiation power inversely proportional to black hole mass, squared meaning smaller black holes evaporate faster while supermassive black holes evaporate incredibly slowly, taking durations exceeding Google years for complete evaporation. Stephen Hawking's 1974 theoretical discovery that black holes radiate fundamentally changed understanding of black hole thermodynamics and ultimate fate. Black holes possessing temperature inversely proportional to mass, approximately 60 nanokelvin times solar mass divided by black hole mass, stellar mass. Black hole 10 solar masses having temperature roughly 6 nanokelvin, far colder than cosmic microwave background currently 2 0.725 Kelvin, meaning black holes currently accreting background photons and matter growing rather than evaporating net. But as universe expands, background radiation temperature drops exponentially redshifting photons into negligible energies, eventually perhaps around 10 to the power of 20 years, background temperature falling below black hole temperature, allowing net evaporation proceeding. Though even then extraordinarily slowly, tiny primordial black holes, if existing with masses below roughly 10 to the power of 11 kilograms, already evaporated by present epoch, producing gamma-ray bursts potentially observable. Stellar mass black holes beginning significant evaporation only after universe age exceeds roughly 10 to the power of 67 years depending on exact mass. Supermassive black holes much later around 10 to the power of 100 years for billion solar mass black holes. You watch black holes slowly evaporating over unimaginable timescales beyond human comprehension, hawking radiation emitting photons, particles, one by one randomly. Quantum fluctuations at event horizon creating virtual particle pairs where one particle falls into black hole negative energy relative to infinity, while other escapes positive energy carrying away mass energy from black hole, effective temperature and luminosity extraordinarily low for macroscopic black holes, making detection impossible even if close enough to observe, mass decreasing infinitesimally slowly, initially accelerating gradually as mass decreases, temperature rises, and radiation rate increases, following inverse square law. Stellar mass. Black hole, 10 solar masses, requiring approximately 10 to the power of 67 years, completely evaporating far exceeding current universe age. 10 to the power of 10 years by factor 10 to the power of 57 incomprehensibly long, even compared to trillion-year stellar remnant lifetimes. Supermassive black hole, billion solar masses, requiring roughly 10 to the power of 100 years, evaporating beyond Google timescale, approaching Googleplex durations, final moments of evaporation proceeding rapidly as tiny black hole, just kilograms remaining, radiates furiously, temperature rising to billions of Kelvin emitting high energy particles and gamma rays, final evaporation, releasing remaining mass energy in brief intense flash, equivalent to millions of nuclear weapons detonating simultaneously, leaving nothing but radiation dispersing spherically outward into infinite space, fading through redshift, black hole information paradox, questioning whether quantum information initially falling into black hole, lost permanently in evaporation, violating quantum mechanics' unitarity principle, or somehow preserved through subtle quantum correlations in Hawking radiation spectrum, allowing information conservation though mechanism remains unclear, debated among physicists. By 10 to the power of 100 years, approximately Google years, incomprehensible duration exceeding trillion years. Even largest supermassive black holes evaporated completely through patient Hawking radiation, universe containing only radiation photons, neutrinos, electrons and positrons. If protons decayed, possibly stable subatomic particles, depending on particle physics details, all particles becoming increasingly isolated as expansion dilutes densities exponentially towards zero. Typical particle separation growing to cosmic horizon scale light travel distance as dark energy's exponential expansion dominates, completely overwhelming all other forces. Accelerating expansion ensuring widely separated particles never encounter each other again throughout remaining eternity, each particle existing in isolated causal bubble. Completely alone in infinite expanding space unreachable by any other particle light signal or influence. Temperature approaches absolute zero asymptotically as photons redshift, continuously stretching wavelengths into negligible energies approaching infinity. Wavelength, cosmic microwave background radiation cooled through expansion from current 2.725 Kelvin to femtokelvin, nanokelvin picokelvin, arbitrarily small temperatures approaching zero, asymptotically never quite reaching, wavelengths stretching to horizon scale, making individual photons fundamentally undetectable, requiring detectors larger than observable universe, effective temperature approaching zero, though never precisely reaching due to quantum, mechanical zero-point energy preventing absolute zero achievement, entropy approaching theoretical maximum as energy distributed uniformly across infinite space with no remaining gradients anywhere. No usable energy remains anywhere for doing work or driving irreversible processes or sustaining complexity or organization, perfect thermodynamic equilibrium achieved completely. Heat death realized, second law of thermodynamics ultimate victory. Universe exists in state of maximum disorder, with no distinguishable structure or organization or activity or change. Quantum fluctuations continue, despite apparent emptiness, vacuum constantly bubbling with virtual particle pairs, spontaneously appearing and annihilating within Heisenberg, uncertainty principle, time limits, occasionally random fluctuations producing brief, localized decreases in entropy, Boltzmann brains representing hypothetical conscious observers arising spontaneously from random fluctuations, assembling organized structure briefly before dissipating back into chaos. Probability of Boltzmann brain forming arbitrarily low, but given infinite time becomes certainty, raising philosophical questions about whether we might be Boltzmann brains rather than evolved biological entities, though anthropic reasoning suggests structured universe more likely producing evolved observers than spontaneous brains. False vacuum decay represents possible universe-ending scenario if our vacuum state not true, minimum energy configuration, but metastable false vacuum vulnerable to quantum tunneling into lower energy. True vacuum, tunneling probability per unit volume, per unit time, extraordinarily small but over infinite time and infinite space becomes probable. Vacuum decay, bubble nucleating somewhere, expanding at light speed, converting false vacuum to true vacuum, phase transition, releasing enormous energy, potentially destroying all structure and rewriting physical laws within bubble. Bubble expansion, unstoppable once started, eventually consuming entire observable region and beyond. Though if vacuum stable, then universe persists indefinitely in heat-death equilibrium. Dark energy's nature determines precise ultimate fate. If cosmological constant, then exponential expansion continues forever isolating structures completely within cosmic horizons. If dynamical field potentially varying with time, then future evolution uncertain. Depending on field's properties and evolution, possibilities include Big Rip, where dark energy density increases, causing expansion, accelerating catastrophically, tearing apart galaxies, then solar systems, then planets, then atoms, then nuclei, then quarks until space-time itself tears apart at finite future time. Or Big Crunch if dark energy reverses becoming attractive, causing recontraction collapsing universe back to singularity, though current observations suggest expansion accelerating, making crunch unlikely. Assuming cosmological constant, universe expands forever approaching de Sitter space geometry, exponentially expanding spacetime with cosmological horizon approximately 10 billion light-years radius, beyond which nothing ever observable. Structures within horizon eventually evaporating through Hawking-like de Sitter. Radiation, though, process extraordinarily slow-taking, googolplex years or longer, ultimately even de Sitter space potentially decaying through quantum tunneling to different vacuum state with different physical constants, potentially supporting different forms of structure and possibly consciousness, though entirely speculative. Cosmic perspective reveals our existence occurring during brief interval when stars shine and galaxies cluster visibly. Stelliferous era lasting roughly 100 trillion years from first stars igniting around 100 to 400 million years. Post-Big Bang to last red dwarf deaths around 100 trillion years future, representing approximately 1/10 quintillionth of universe's total timeline. If proton decay occurs around 10 to the power of 34 years timescale, infinitesimally brief moment of brightness and warmth and complexity surrounded by eternal darkness and cold, and simplicity preceding and following, vast eons before stars, when only hydrogen, helium, lithium drifted through expanding space, cooling gradually, waiting patiently for gravity, slowly assembling first structures from density perturbations frozen during inflation, then stelliferous era's fleeting brilliance, barely 100 trillion years compared to Google. Years of darkness following after last stars die, and stellar remnants cool and black holes evaporate, leaving nothing. Yet within this brief cosmic summer complexity emerges building upon itself through hierarchical structure formation, atoms organizing into molecules, organizing into self-replicating systems, organizing into cells, organizing into multicellular organisms, organizing into ecosystems, organizing into technological civilizations, organizing into unknowable futures, life and consciousness, representing universe's most intricate achievements, arising during narrow window when energy gradients sufficient driving complexity against entropy's relentless increase. Consciousness itself, perhaps universe's supreme accomplishment, matter organizing, sufficiently experiencing subjective awareness, capable contemplating cosmic timeline, appreciating our fortunate existence during this illuminated era rather than eternal darkness before or after, beauty found in transience precisely because temporary and precious and irreplaceable, each conscious moment representing universe experiencing itself subjectively through temporary assemblages of atoms pondering their origins, destinies, meanings, purposes. You now float in universe trillions upon trillions of years future, darkness absolute and complete, no light sources anywhere across infinite space, temperature indistinguishable from absolute zero, all black holes evaporated, all protons decayed if decay occurs, all matter dissolved into radiation redshifted into invisibility, maximum entropy achieved, no gradients driving change, no energy available for work, no processes occurring, no events happening, only eternal unchanging void stretching infinitely in all directions, time losing meaning without change to measure it by, universe achieving perfect equilibrium. Silence reigns completely, no sounds possible in vacuum, nor mechanisms generating sound. Darkness total without light sources or light reflecting matter, cold absolute approaching zero. Kelvin asymptotically, emptiness infinite, with particles separated by cosmic horizon distances unreachable by any signal travelling at light speed. Loneliness ultimate, as any remaining structures exist in isolated bubbles, completely cut off from rest of universe, each structure alone in infinite expanding space, unable ever contacting anything else. Yet perhaps within this desolation, occasional quantum fluctuation produces brief spark of organization, random chance assembling temporary structure before inevitable dissipation. Boltzmann brains momentarily experiencing consciousness before dissolving, fleeting islands of order in infinite sea of chaos, each appearance independent and isolated, never aware of others, never building cumulative knowledge, never progressing toward any goal, just brief flickers in eternal night signifying nothing, persisting nowhere, accumulating no legacy. From initial singularity through cosmic inflation, expanding space exponentially through radiation domination, creating first atoms, through matter domination, allowing structure formation through dark energy, domination, accelerating expansion toward heat, death equilibrium, universe traces arc from minimal entropy, at beginning through increasing complexity, mid-timeline toward maximum entropy. At end, entropy arrow defining time's direction. As disorder increases, second law of thermodynamics playing out across cosmic scales as concentrated energy in Big Bang disperses into uniform distribution. Approaching perfect uniformity, life and consciousness representing temporary local entropy. Decreases sustained by external energy influx from stars themselves burning down universe's usable energy budget, hastening ultimate heat death by converting concentrated nuclear energy into dispersed thermal radiation. Perhaps this isn't the end but transition, oscillating universe models suggesting big crunch followed by big bounce, starting new expansion cycle, though current observations suggest eternal expansion more likely. Multiverse theories proposing infinite universes with varying physical constants, where our universe merely one bubble among infinite collection each with own history and fate, some supporting life, others sterile, anthropic selection requiring we find ourselves in life. Permitting universe regardless of how rare such universes might be in larger multiverse, our universe's parameters appearing finely tuned for complexity, possibly because only such universes produce observers capable questioning their existence. Such universes, eternal inflation models suggest inflation never completely ends anywhere. While our observable universe exited inflation creating structures and eventually observers, inflation continues elsewhere eternally producing infinite universe bubbles, each beginning their own post-inflationary evolution, infinite variety of conditions and constants realized somewhere in infinite multiverse, every possibility occurring infinitely many times across infinite space, our observable universe representing infinitesimal fraction of infinite reality. Implications suggesting everything possible happens somewhere, though separated by unbridgeable distances and untraversable expansion rates, preventing communication or travel between different bubbles. Quantum mechanics' many worlds interpretation proposes reality constantly branching into parallel universes representing every possible quantum outcome, each measurement or quantum event splitting universe into multiple copies realizing different possibilities, infinite constantly proliferating universes exploring all possibilities simultaneously, consciousness experiencing single branch, while other versions experience different outcomes in parallel realities. Interpretation solving measurement problem, avoiding wave function collapse, but postulating enormous ontology of parallel realities, all equally real though mutually unobservable, philosophical implications profound, suggesting every possible history occurs somewhere in infinite quantum multiverse. Final meditation upon cosmic timeline reveals profound beauty in transience and impermanence, matter organizing briefly into structures supporting complexity, consciousness life before inevitable dissolution returning to equilibrium, brief flowering of awareness representing universe achieving self-reflection temporarily, cosmos experiencing itself subjectively through temporary assemblages of atoms contemplating their origins and fates and meanings, meaning found not in eternal persistence, impossible given thermodynamics, but in temporary existence's preciousness, precisely because temporary and unique and irreplaceable, each moment in cosmic timeline representing singular occurrence never repeated exactly, each conscious experience representing universe aware of itself locally briefly, consciousness's appreciation of beauty, truth, love, knowledge representing universe, achieving self-awareness, fragmentarily, before returning inevitably to darkness. Equilibrium, perhaps ultimate cosmic purpose. Being experience itself, awareness arising, existing, appreciating, wondering, questioning, loving, creating, suffering, enjoying, then passing, completing cosmic cycle from quantum potential through classical actualization, through structure formation, through consciousness emergence, through experience, through dissolution, returning to quantum potential, Ouroboros swallowing its tail, eternal return, cycle completing, then possibly beginning again in different form, different universe, different physical constants, different possibilities, or perhaps ending permanently, heat death final, ultimate unknowability of what lies beyond current cosmic horizon temporally or spatially or conceptually, mystery permanent and inviolable, consciousness confronting unknowability with wonder and humility and acceptance. You float in heat-death universe, experiencing final cosmic state, perfect uniform black extending infinitely in all directions without variation or feature or landmark, no light sources anywhere across infinite space throughout infinite time, no photons carrying sufficient energy for detection, no heat gradients driving thermodynamic processes or enabling work extraction or sustaining commons, leaving only radiation stretching across infinite space, temperature approaching absolute zero, wavelength reaching cosmic horizon scale, universe achieving maximum entropy, possible, perfect thermodynamic equilibrium realized throughout infinite volume, no usable energy remaining anywhere for performing work, or generating complexity or sustaining consciousness, or driving any processes whatsoever. Eternal cosmic stillness achieved permanently, no change occurring anywhere ever again. Time losing meaning without change to measure its passage, perfect equilibrium eternal and complete, sleep now in infinite cosmic peace. Perfectly safe equilibrium surrounds you infinitely in all directions. Drift gently with universe into eternal dreamless rest, cosmic silence welcoming you home into Absol.